fixed bias circuit, or it is also known as constant base current. In this biasing, we have connected our common emitter transistor in this manner. This is VCC, which is supplied to RB and also supplied to RC. This is higher potential, so in NPN transistor, this P side is connected with higher potential and this collector is also connected with higher potential, and this emitter is ground, which is N type. In that case, base emitter is forward while base collector is reverse bias. Now, this is RB, resistance provided to the base, and this is RC, resistance connected to the collector. The use of resistance RB provide to the proper forward bias voltage across the base emitter. A major portion of voltage from the battery VBB is dropped across the resistance. The positive terminal of both the battery VCC and VBB are connected to the resistance RC. Now, we will analyze this circuit using Kirchhoff's voltage law. So first of all, we will consider that VCC is supplied at this point and this is the potential which is supplied to RB, and this circuit we will consider. In that case, here the current will be IB, then draw the current IB, and here current will be IC. Then we can write VCC minus, this is positive and this is positive and this is negative, so that's why minus IBRC minus potential drop across base and emitter VBE equals 0. From this equation, IB is equal to VCC minus VBE upon RB. So, IBRC equals VCC minus VBE and IB equal to VCC minus VBE upon RB. Now, base emitter voltage, this is forward bias junction, so VBE equals 0.7 volt for silicon or 0.3 volt for germanium. In that case, we can neglect this voltage, then IB will be equal to VCC upon RB. VCC and RB are kept fixed, so that's why base current will be fixed. Why? This fixed bias circuit is known as constant base current because VCC, value of VCC is fixed, and RB, the resistance applied to the base, is also fixed, so that's why IB will be constant. IB is constant. Because VCC and RB is not being changed. Now, collector current. Next point is collector current. collector current IC is equal to beta time of IB, where beta is the current gain. In this relation, we have neglected the reverse leakage current, because the value of reverse leakage current, that means the current due to the minority charge carrier, is too small. Then again we will apply Kirchhoff voltage law for this circuit. Then VCC minus ICRC minus VCE equals 0, where VCC is the collector emitter voltage, VC is voltage between collector and emitter. It is obvious from this relation, supply voltage VCC is always greater than ICRC. Thus, for the transistor to be biased in the active region of operation. So from here we can conclude that VCC is greater than ICRC, because VCC minus ICRC minus VCE is equal to 0, then VCC is VCE time greater than ICRC. So that's why VCC is greater than ICRC, then IC will be less than VCC upon RC. So our transistor will be in active region. Transistor will be in active region. Thus, calculating IC, it must be ensured that this relation should be satisfied. It means that when we will calculate our IC and the value of IC is less than VCC upon RC, in that case transistor will act in saturation region, of active region. If IC exceed the value, if this condition is satisfied, then it will be in active region. If IC is greater than VCC upon RC, then transistor will be in saturation region. So VCC minus IBRC minus VBE is equal to 0, then IB equal to VCC minus VBE upon RB. As we know that base emitter is acting as a forward bias PN junction diode, and the junction potential VBE equal to 0.7 for silicon and 0.3 for germanium. In that case, base current IB is equal to VCC upon RB, because VCC is higher than this voltage, so that's why we have neglected VBE. IB is constant because the VCC applied and the RB is fixed, so that's why value of IB is constant. Now collector current, in this case IC equal to beta time of IB and plus ICO, which was the minority current, so that's why VCC minus ICRC minus VCE equal to 0 for this circuit. And from here we are concluding that VCC is greater than ICRC, so IC is less than VCC upon RC. If the value of IC from here is satisfying this relation, in that case we will say that our transistor is in active region. If the value of IC is greater than VCC upon RC, then transistor is acting in saturation region. Now next point, From our relation, we can write down VCE, voltage across collector and emitter, is equal to VCC minus IC RC. From here, VCE is also constant because collector current is VCE is constant, so that's why collector current is also constant. So on keeping VCC and IC fixed, the operating point is fixed. This circuit is not often used as it does not provide protection of change in IC due to heating of transistor. It does not provide protection for change in IC due to heating of transistor. The operating point in the fixed bias circuit can be determined by first process, calculating base current, IB. Second point, current IC is calculated by beta IB. This value should not be greater than VCC upon RC. Now we have discussed that how we find the base current and collector current, and how we will see that this transistor is working in active region or in saturation region. Then we will determine its quiescent point or operating point by calculating base current and then collector current with this relation, and this collector current should be less than VCC upon RC. Our next point to discuss this fixed bias circuit is its drawback. Next point is drawback. What is drawback of this fixed point circuit? Now in this, it's easy to find IB and IC and with this operating point. Where transistor is acting in a active region. By simply change the value of RB, the second and the third requirement of proper biasing is not met. That's mean if we are changing RB and RC, then behavior of current will be changed, so operating point will not be fixed. When the temperature increases and also due to increase in temperature, increase in temperature, IC will change while IB is fixed. It's mean that according to IC is equal to beta IB, the gain factor will be changed. So this is a fixed bias circuit in which we have found it first of all base current and then collector current, and why it is known as constant base current circuit, because we have used a fixed value of resistance at the base and the potential across base and emitter was constant, and it is constant, that is 0.7 volt for silicon and 0.3 volt for germanium. So that's why IB was equal to VCC upon RB. We have neglected the VBE and then we have founded the collector current. Then we have discussed about the operation mode, that it is acting as an active region or it is acting in saturation region. How can we define? If IC is less than VCC upon RC, then it is in active region. It is working in active region, and when IC is greater than VCC upon RC, it is working in saturation region. Okay, thanks.